Welcome back. Today we're going to discuss the topic of graphing linear equations. Last lesson, we discussed how there existed in the 1560s a man named René Descartes. And René Descartes is important to the field of mathematics, the entire field of mathematics, but also to the entire Western civilization, meaning every country from Russia westward who follows what is known as a Western paradigm of thought has been influenced at their core by the ideas that have come out or have been expounded on by René Descartes. And so, of course, one of the ideas that René Descartes discussed is what is known as Neoplatonism. This is simply the idea that when we're looking in the world around ourselves, there exist different types of phenomena that we might be observing or interacting with. Some phenomena are physical in nature and lend themselves to physical solutions and or physical modes of understanding and or interpretation. An example of this would be things that are amenable to the scientific method, meaning rational processes that we might see in the world around ourselves that we might then perform an experiment upon in order to determine what exactly composes this or that phenomena. This would be an example of something that we can come to know in the sense of uh, the thing itself existing in our ordinary material world around ourselves. But then there are phenomena that, to the extent that these phenomena exist at all, we can only say that the phenomena are metaphysical, if you will. Like, for example, this idea that a triangle actually exists. Well, we might be able to put, say, three dots on a page, and we might connect those dots and say something with three dots and that has intersecting lines such that, the angles of the sides always add to, say, 180 degrees. This is the object defined as a triangle, but you won't actually be able to see a triangle in the world around ourselves. Okay, and so we would say that the triangle, the perfect triangle, if that thing should exist, must certainly not exist in our material world, but may perhaps exist in some sort of transcendent reality, if you will. Okay, so that was the first idea that René Descartes brought. And the importance of this idea is to separate out things that are of a spiritual nature or that have an ascetic quality to them, if you will, or perhaps things that are not phenomena that are totally rational. So, for example, how music makes you feel, that would be an example of a phenomena that's not totally rational, right? Um, these types of things we might be able to classify as certain types of truth, and by doing that we then are able to discover other truths about the world that maybe we can in fact investigate through our material means through what is known as empiricism, which is the second great idea that René Descartes brought to the table, because in his great works on the methods, he essentially invents the idea of the scientific method. And along with the works of Newton, if you combine both of these two intellectual giants together, you get more or less the process that we come to know as the scientific method, where, Rene Descartes would say that you need to, if you're looking at some sort of a material phenomenon, you need to observe that phenomena. You can then run tests on the phenomena in order to determine how the phenomena behaves. You then think about and or hypothesize. You create a guess as to what you think is happening with the thing that you're observing, and then of course you determine whether or not your guess was correct or not. And this is an iterative process, meaning it happens over and over and over and over again as you continue to refine your understanding of the world around yourself. You don't have a termination point in empiricism. There's no definite answer that you obtain using the scientific method. Science is not, as people like to believe in the modern times, is a very popular belief. It's not antithetical. It's not against religion. Science is a tool set that you use to come to know certain aspects of the world around yourself. It doesn't invalidate, the metaphysical, because the metaphysical is not amenable to the kinds of analysis that would be uh, that works with the scientific method, to be clear. Um, so that being said, in back in the day, in the 1560s and the 1600s, philosophers who were coming to the table, they would often confuse these ideas together. They would often confuse this, science and spiritual phenomena together with one another. And so to have a philosopher who was really able to separate the two out into different modes of thought and or different modes of investigation and philosophical inquiry was an incredible feat indeed. And this is what Rene Descartes did. And the third thing that Rene Descartes did, which again is what this lesson is all about, is that he was able to discover that geometric phenomena, to the extent that you can be able to represent some sort of a problem statement in terms of geometry, the geometric phenomena in and of itself can be then represented in terms of algebra. And so this is important because if we are examining phenomena in the world using the scientific method, and then we want to, say, investigate this phenomena, usually that investigation will involve numbers in some way, shape, or form. And so if we can reduce the phenomena itself to some sort of a geometry problem, we can definitely find out what the behavior must be, or we can guess at how things start to work or how things must work, because algebra only obeys certain rules. And if we assume from the get-go that the physical phenomena in the world must be coherent in a similar manner or in an analogous manner to the coherency of algebra, then it's not too much of a stretch to say that if we make an observation about a phenomena, the phenomena itself must also obey the rules of algebra. Now, unfortunately, the physical world is not exactly that straightforward, but that was literally the assumptions being made by Rene Descartes and Newton going forward through history. It wasn't until the 19th century, late 19th century, really, that people started to question whether or not that was true, question whether the physical world, to be specific, actually obeyed the rules of algebra in the way that people thought. And surprise, surprise, it's a little bit trickier than that, unfortunately. So, without further ado, let's discuss the topic of equations. So, if we are, say, making an observation of the world, and say we are observing the boiling of water. Okay, we've got maybe a teapot or just a pot, and here's my lid. And inside this we have some water, and we put the water on the burner. Okay? We might observe that as we perhaps increase the temperature, the amount of energy going into the water increases. Now, students might say, well, how would we observe the amount of energy in the water increases? Well, we might say that, when the water is just water, there's no energy added to the system, so it's just water. And then when you start adding heat, you're adding whatever causes heat to be hot, which we presume is energy. And so, if we're taking the temperature of the water from, say, a starting point to, say, some other point here where we're increasing the temperature, we might then say that, there's a corresponding increase in the amount of energy that is being imparted to water itself. Okay, so say we have this idea that as we increase temperature, the amount of energy is being that's being imparted to the water increases itself. So we might be able to draw out one axis representing temp or temperature. We might have another axis, maybe a vertical axis, which represents the energy of the water itself, the state of the water. And then from this graph, this diagram, where we're somehow measuring the energy of the water, maybe we're measuring the amount of evaporation taking place, and we somehow define energy input as uh, the amount of thermal heat that is required in order to, say, evaporate a certain amount of water. Maybe that's how we define energy. I'm not exactly sure. Okay, there is in fact a way that the scientists have defined energy, but as this is just an example, it's not too important. And perhaps we discovered that there are certain, say, physical properties that also influence the rate at which, when we increase the temperature, the energy increases. Perhaps the area of the pan that we fill with water is important, is one of the variables. And then perhaps, so this A perhaps is represented by area. And then perhaps, if instead of water we used, I don't know, oil. We discover that it takes a lot less energy to get a vaporized state. Perhaps instead of having to put our pan on the burner for a number of hours, it in fact is a much faster amount of time before the water starts to boil. And so we have perhaps another variable, or another, what is called a coefficient, which we call the heat coefficient, and that is just some sort of an adjustment factor to adjust for the fact that we might be, dealing with oil instead of water, or whatever liquid that we might be, filling our pot with. Okay, so the point is that this thought experiment of observing the water that's boiling and increasing the temperature, and then defining maybe some sort of corresponding process we call energy. This is of course how science actually works in the real world. And um, you're actually able to create these diagrams, if you will, which represent the geometry or the behavior in this instance of the amount of energy of the water itself as you increase the temperature in this instance. And of course, this is just an example. So, of course, in mathematics, we're not necessarily interested in the particular example cases. If, for one thing, many students may not be interested in, say, how thermal fluids work, or how heat transfer works into a fluid or throughout fluids, right? And then for another thing, we may want to perhaps generalize the process of being able to analyze the geometry of something. So instead of just focusing on, say, an energy equation, which is what we have written here, we might want to generalize this idea that could apply to perhaps more problems than just a single case study of energy. Perhaps we might want to apply what we learned to finance, or what we learned to statistics, or what we learned to any number of other applications in the world around ourselves. And so this is exactly how a mathematician might think. He might start with, say, something that he can observe in the world around himself. He tries to think of some sort of a model of how that process works. And then the mathematician goes about trying to generalize what behavior might exist in this something. And the way that we generalize behavior is rather straightforward. And in mathematics, whether you're taking this class or any other class in the future, you're going to see equations which look something like this. Okay, you're going to have, say, a y variable. Usually you might have an equal sign somewhere in your equation, and then on the right or the left side of your equal sign, you're going to usually see some sort of an x, and x may be multiplied or added with some sort of some other terms, if you will. And the way in which we are supposed to interpret this expression is that, first of all, we have to know whether a variable in our expression is what is called an independent variable or an endogenous variable, and whether a variable in our expression is something that is a dependent variable or an exogenous variable. Now, let me explain those terms. So, when we say independent variable, What this word means is it's analogous to pushing the buttons on a computer program. So when you say an independent variable, you might have different buttons on a computer program, okay? For your computer or for your game console, whatever, for your cell phone. You might have different buttons on the cell phone, right? So you might have, say, the button A, you might have this button B or the button C. And basically, you as the user get to choose between these different options, whether it be A, B, or C. But once you choose one of those options, you kind of set the performance or the behavior of the machine in motion. So the machine's going to do some sort of a task for you, some sort of a work, and then you get some output from that. When we say an independent variable, we're talking about some sort of a phenomena where we can actually change these input parameters. We're talking about the input into a system, okay? I also used a fancy Latinate word. I said endogenous variable. This is a Greek word. Endo just means in. Genus means family. So, and it means basically the behavior inside of the system that's causing the properties that you're witnessing to emerge. So, what does it mean? It means if we were witnessing water boil, the question we would ask is what is causing the water to boil? And so we might say that this heat that's being added to the water, that's coming into the water, the temperature increase resulting from the heat, rather, coming into the water, or the heat transfer into the water specifically, the increase in temperature is causing some sort of an increase in the apparent energetic nature or state of the water itself, which is then once you pass certain threshold, you get boiling instead of boiling and steam instead of just a calm pot of water, if you will. So we would say that temperature in that instance is a endogenous, it's inside the system. Whereas the word exogenous is the opposite. It means outside. And genus means the family. So the exogenous state of the water would be, if you're witnessing this pot, initially you see, when you don't have the pot of water up, on the burner itself, the pot of water is perhaps it's calm, it's at a calmer state. And then once you've applied the pot of water to the heat, you start seeing that the water turns into steam. And so the apparent effects of the change or the output, if you will, of your environmental state, whatever is happening inside of your machine, inside of your pot, you might not be able to see inside of the pot because you have the lid on the pot, right? But whatever is happening inside of the pot, you are able to see the effects of that, if you will. And so that is what we mean by exogenous and or the dependent variable. Once you pick the inputs into this system, the dependent variable depends on those inputs, or said another way, the output of the system changes. And so whatever variable is representing the output of the system, that is your dependent variable. So I'm going to say output over here. That's dependent variable. It means exogenous. Endogenous variable just is the same thing as an input into the system. It is what values can actually change. And by making a change there, you change everything else. And this is also the independent variable. So when you're just given some random equation like y is equal to 4x plus 3, and you have no context for what this equation is supposed to represent, either y or your x in a technical sense could represent either your independent or dependent variable. However, in the context of algebra, and specifically this textbook, your x is always assumed to be your independent variable. I won't draw it like that. That looks a little bit weird. But your x is always assumed to be your independent variable, and your y is always assumed to be your dependent variable. Okay. So what can we use these equations to do? That would be the first question I would ask. Well, for one thing, whenever you do actually have a situation where you can express a physical phenomena in terms of a equation, this is really, really nice because if you actually want to know what the behavior of your system is just from the equation itself, all you have to do is you give yourself a number of points to play with. What do I mean by points? I'm saying X is the independent variable. It is the input into your system. Once you pick a input into the system, you're going to lock the machine into motion. The machine will do something and it will produce your output, your Y. So if your X is your input, now, naturally, students would say, well, I don't know what the input into the machine should be. How should I know what I can put into the machine? And I'm going to make it very simple for my students. You can pick whatever inputs you want into your machine, but why not pick easy inputs for the machine if you're just interested in the overall behavior of the machine itself and you don't actually care about some sort of particular circumstance inside the machine. So you're going to basically give yourself a table. You're going to write at a table of points. In my left column, I'm going to represent that I'm changing my X value from -1, 0, and 1. And in my Y column, I'm going to represent that I'm performing a calculation using the equation I'm given. So in this instance, I'm going to say take -1, which is the value for my X. I'm going to plug it into my equation where you see the X itself. And I'm going to perform that calculation. Positive and negative is a negative. -4 plus 3 gives me -1. We're going to continue doing this calculation for each point we have. And eventually, we're going to be left with no more points left. Okay, so we have a new table that we've generated. We said -1, 0, and 1 is our X values, but then the corresponding Y values that we've calculated are -1, 3, and 7. And what this represents on the Cartesian plane is it's going to represent this idea that along the horizontal line, you can go to the right or to the left. And if we go to the right, we're going in a positive distance. And if we go to the left, we're going in a negative distance. And if we go up, we're going a positive distance. And if we go downwards, we're going in a negative distance. So what these numbers represent is actually represents points along the line or along the geometry that represents the behavior of the system that you might be analyzing. So this -1 for my X actually represents that we have a point where it exists a little bit to the left of your Y-axis. And if we have a Y corresponding Y value of -1, we have a point right there at what is known as -1, -1, which brings me to a second point that we need to make. This value here is what is known as our X coordinate. This value here is what is known as our Y coordinate. Because both coordinates are the same, it's easy to get confused, but the Y coordinate doesn't actually have to be the same as the X coordinate. In fact, it won't be the same for any of our other points. So in this case, it just happened to be that for our -1, for our choice of -1 as our X value, Y was a corresponding -1. But if we picked 0 for X value, we actually found that our Y was in a +3 direction. So you're starting at 0, which would be right in the middle of the axis. If we were to go up 3, we'd find that there is another point that is exactly 3 above the axis itself. And so At this point, if you wanted to draw a line, you could, but we have another point that's at our disposal. So, and this point is at 1, 7. So if we go to the right one, which is a horizontal distance of 1, and then we go up 7, we find that we're at this point here. Okay, so to recap, we observe the physical world. Okay, usually using the scientific method, we come to a decision about what phenomena is supposed to represent in terms of algebra. We then have some sort of an algebraic equation that we might be able to use to model this scenario. And then if we actually wanted to know the geometry of the behavior illustrated, if we wanted to illustrate the behavior rather of this phenomena, we can simply give ourselves some values for x, and then because x is the input into our machine, quote unquote, or into our model, when we have an x point, we then just perform a sequence of calculations to acquire our y value or corresponding y value. And then with the x and the y point, we plot on our graph the sequence of points and then draw a straight line through it. And we arrive at our geometry. In this instance, y equals 4x plus 3 is a line that goes up into the sky. All right, let's look at another example, shall we? Suppose we have y is equal to negative 5x plus 2, and we want to figure out what the graph of this corresponding line happens to be. Here again, we're going to just give ourselves some easy points. Don't make your life more difficult than it has to be. You could pick any 3 points. In fact, you could pick just 2 points if you wanted to, and they can be anything you want them to be. I tend to pick a point on the left and on the right side of your y-axis. So since I know that -1 as an x value will be to the left of my y-axis, and I know that +1 will be to the right of my y-axis, I'm going to pick these points because that's going to allow me to identify the behavior of where my line or where my graph might pass through the y-axis itself. Okay, which is going to be important here when you get to section 3.4. For now, it doesn't really matter that much, but you'll see why I'm doing it when we get to section 3.4. So at any rate, we pick -1, 0, and 1, and this locks in the behavior of our machine. So for y, for example, we're going to evaluate this equation where we have -1 for our x value. Negative is a positive, so we'll have positive 5 times 1 is 5, plus 2 gives me 7. And then we're going to do the same thing for 0. We'll have 0 plus 2, which gives me 2. And we'll have -5 times 1 plus 2, which gives me -5 plus 2, or -3. And so if we were to plot these points out, we've got -1, +7, 0, 2, and 1, -3. If we draw a line through all of the points, we would find that we have a straight line that goes down to the ground. Now, students might ask at this point, how do I know that the behavior of the line will continue down into the ground or up into the sky? Okay. It's a reasonable question. They're like, how do you know that this doesn't, turn back on itself somewhere? And I know that it's not going to turn back on itself because we are actually dealing with a special type of equation. We're dealing what is called a linear equation. So a linear equation always has a general form. Y is equal to mx plus b, where m is what is known as your slope, b is known as your y-intercept. X is, of course, your independent variable, and y is your dependent variable. And when I say linear equation, linear, the root of linear is just line. So it means an equation that has line-like behavior. So yes, indeed, this y is equal to negative 5x plus 2 will, in fact, be a line, and it will go down straight into the ground, or up into the sky to the left. All right. Sometimes this equation is known as the slope-intercept equation, because it can be used in order to construct a specific type of line given some input parameters. So for example, you might have a question. And the question might say, find the equation of a line whose slope is -3 and whose intercept is 2. And the question is, well, what equation would that be? So just like with our word problems that we had earlier, last chapter, you're going to scan this particular word problem for keywords that are important to solving it. First of all, if you have a problem that's asking you to find an equation, you should naturally ask yourself, what kind of equation are you finding? In this instance, it tells you find the equation of a line. Okay, cool. So your mind should already be thinking, okay, this is y equals mx plus b type situation. I'm trying to find an equation of a line. What am I trying to do? I'm trying to get y equals mx plus b. Okay. But then you're like, okay, what is my m? What is my b, right? Well, in this instance, it tells you the slope is -3 and whose y-intercept is equal to 2. So we look to our equation, the equation of the line, and we ask ourselves, well, what parameter represents what letter, what value represents the slope? And we would say the slope is represented by this m term, this coefficient, this number that will usually be in front of our x. And then what is the y-intercept? Well, the y-intercept is the number that is either being added or subtracted from the x term. So in this instance, we would say our y-intercept is going to be our b term, our m is going to be our slope. And so we take our equation, we rewrite it, and where you see your m, you're going to put the -3, and where you see your b, you will put the number 2. Excellent. And this would be your answer. Your second question might be, find an equation of a line whose slope is -2/5 and whose y-intercept is 5. Here again, you're going to read this problem statement, find the equation of a line whose slope is -2/5 and whose y-intercept is 5. You're going to come across the keyword line. Your mind should be thinking y equals mx plus b is a equation that represents a line in this instance. This the linear equation that we're going to need. And we're given a slope as -2/5. So we know our knowns. We know the slope is -2/5, or this is also our m value. What else do we know? We know the y-intercept, or the b, is equal to 5. So we're just going to plug in our terms. Where you see an m, we're putting -2/5. And where you see the 5, you're going to plug in your 5. Now, if the question then asked you to draw out the geometry or draw out the corresponding behavior of the line, the graph, if you will, of the line, that is the result of um, one whose slope is -2/5 and it has a y-intercept of 5, then what it's asking you to do is it's asking you to not only find this equation, but you've got to create yourself a little table, give yourself some points, -1, 0, and 1, and then you're going to plug in the points into where you see your x. Okay, in this instance, we would find that for -1, for the value -1 as an input, you would get an output of 27/5. For an input of 0, you would get an output of 5. For an input of 1, you would get an output of you would have -2/5 plus 25/5 is equal to 23/5. All right. So at the end of the day, give yourself a graph. You're going to plot -1 and then 27/5 because that was our first point. We have -1. And students might say, "Well, where's 27/5 on the chart, right?" Well, there's a couple of different ways we could find where 27/5 is. You could, of course, divide 5 into 27. 5 into 25 goes 5 times. So you can subtract and get 2, and then give yourself a decimal, drop it down. 5 into 20 goes 4 times. You get 0. So basically, you're at roughly 5.4. So, and it would be a positive 5.4. So maybe somewhere like right there. Okay. So that would be our first point. Since we had a -1 and a positive vertical of 5.4, then we had 0, 5. So at 0, we were up 5. So like that. And then at 1, so this is going to be a really, really quite gracious incline. It's not very steep at all. It's going to be something that looks like this. Okay? This would be our equation of the line. And of course, you need to give yourself enough points to where you can convince yourself that, in fact, the line will go on forever in this direction. I mean, you could try, 2 and -2. If you didn't believe that the line will, in fact, go on forever, you could give yourself 3 and -3. However many points would allow you to convince yourself that, in fact, this line will go on to the right and to the left forever. Go ahead and give yourself those points. Now, this brings us to the next topic. When are we not dealing with a linear equation? When is an equation when and where is an equation not linear? Basically, when we have a linear equation, we're looking for a y is equal to mx plus b style scenario as stated before. But what would not be a linear equation that might at first initially look like a linear equation is you might have something like y is equal to x squared plus something else. This would not, in fact, be linear, not linear at all. And note that it really doesn't matter what side of an equal sign you're dealing with, right? Like the textbook could try to say do some rearrangement by say adding a negative x squared to both sides of your equal sign. And what's going to happen is, they're just doing this to confuse you. This would still be it would basically be the same equation as be above, and for that reason, you would not be dealing with a linear equation. Okay. Other examples of nonlinear equations that you might see would be y is equal to 1 over x. This is this is not linear either. And in fact, it's what is known as a asymptotic function. Okay, because it like has some weird behavior. So this is definitely not linear. But basically, anytime you have an x that's raised to a power, if you see a power which is greater than 1, then that means not linear. Automatically, that's not going to be a linear equation that you're dealing with. Now, some of the trickier problems they might be given, you might be given something like x minus 15 is equal to 0. Is this a linear equation? And the answer that you should say is yes, this is in fact a linear equation because on the one hand, you need to think back to your LEOVs, and we said that we had linear equations of one variable. So we were dealing in the last chapter with bunches, with a wide variety of different types of linear equations. So we were dealing with linear equations there. If you saw one in this chapter, you are definitely still dealing with a linear equation as well. Now, note that there exists some interesting behaviors of lines. So, for example, whenever you have a linear equation, the linear equation will generally pass through the y-intercept as well as an x-intercept. What's interesting is that whenever you're given an equation of a line, such as y is equal to negative 2/5 x plus 5, it's rather straightforward to find a y and x-intercept value. So to find the y-intercept, you need to set x to be 0. To find the x-intercept, we set y to equal 0. Okay, so in this particular equation, when we created the table negative 1, 0, 1, and we found that the corresponding y value for 0 was 5, we actually, what this coordinate tells us is this tells us that 0, 5 is the y-intercept, because this is the point where x is set equal to 0. Exactly. Interestingly, we could also set y to 0 to find out where the line passes through the x-axis. So you'd have negative 2/5 x plus 5. And now what's interesting about this is that you simply are dealing with an LEOV two-step problem statement. And Of course, we have a methodology for solving the LEOV two-step problem statements, which is fairly straightforward. For an LEOV two-step problem statement, you are just going to add your additive inverse to both sides. This becomes 0. 0 plus -5 becomes -5. And what we're going to do at this point is we will use our multiplicative inverse. We're going to multiply by 5 over a -2 and 5 over a -2. Negative is a positive, so you have 5 times 5, which gives you 25 over 2. And this will be equal to 5 times -2 gives you a -10. -2 times 5 gives you a -10. We'll have a -10 over -10x, which is the same thing as 1. You guys need to make sure that you're doing this step because I saw a couple of students that were skipping steps and they were not multiplying by the proper inverse. The only way that you know you're actually multiplying correctly is if this step gives you 1. If you're not doing the above properly, this step where we've got 1 times x will not in fact be 1 times x. Everything needs to make sense, guys. It's not magic, right? Like we need to slow down a little bit. Slow down. Just do things one step at a time. We should get x is equal to 25 over 2. And what does that mean? That means for this particular equation we were dealing with, our y-intercept was 0, 5, but our x-intercept was 25 halves and 0. When you have your y-intercept and your x-intercept, you can always just connect the dots, okay, play connect the dots, and create a line that goes out and models the behavior of a linear equation. So another strategy to plotting the behavior of a line, instead of just giving yourself 3 points, -1, 0, and 1, you would instead say solve for a y-intercept, right? And that would find you the point where you cross the y-axis. And then if you then solve for your x-intercept, you find the point where you cross the x-axis. Then you just play connect the dots and you're able to get the behavior of your line. And then sometimes the line is so straightforward or so easy that you don't necessarily have any really interesting behavior happening at all. So there are a couple of interesting lines that you might encounter in, say, section 3.2, 3.3, and that is when you've got x is equal to some value. You need to remember that when you have an equation where you've just got x equal to something, then if b is positive, you'll have a point b 0, okay, somewhere along your x-axis, and you'll have a line that goes straight up into the air, just like this. That is the line x is equal to some value. So as an example, if we have x equal 3, you're just going to have a line, 1, 2, 3. This is my 3, 0. And I have a line going straight into the sky. Okay. If you have a line y is equal to something, just like before, you have an x and a y axis. And then in this instance, we've got y is equal to some value. Okay. As an example of this, if you have, say, y is equal to 5, you would count up to the point 5. You would draw your line, and there you have it. That is the line of y is equal to 5. Note that when you're graphing your intercepts, you may be given an equation that's in what is called the general form of a line. So the general form of a line looks as follows. It has an ax plus by is equal to c. There's nothing crazy going on here. It just means that you have to do a lot more work to actually find the geometry itself in some instances. It depends on how, I suppose it depends on how you view the situation. But suppose you're given the line 3x plus 6y is equal to 18. And we're asked to graph the equation of a line. Because we're given this equation in terms of the general form of a line, it's actually rather straightforward for us to find its x and y intercepts, because we know that the y-intercept occurs at x equals 0, and the x-intercept occurs at y is equal to 0. So when you're given the general equation of a line, it's, fairly straightforward. If you just want to plug in 0 for your x value, you can then find your y-intercept. If you want to plug in your 0 for your y value, you can then find your x-intercept. And you just have to do a little bit of equation balancing. So uh, going ahead and demonstrating this, we'll plug 0 in for x. We get 6y plus 0 is equal to 18. We get 6y is equal to 18, and we can go ahead and use the multiplicative inverse. Should get 6 over 6y is equal to 18 over 6. Get 1y is equal to 3. And this means y is equal to 3. Okay. Said another way, it means that the y-intercept is at 0, 3, because x is 0 and y is 3. All right, so doing this again, we're going to plug in 0 for our y. And we'll have 3x plus nothing is equal to 18, or 3x is equal to 18. Using that multiplicative inverse, 1 over 3, we will multiply both sides by 1 over 3. You get x is equal to 18 divided by 3. 18 divided by 3 is 6, so x is equal to 6, which suggests that our x-intercept is equal to 6, 0. Now, if we were to draw out the behavior of this line, you would see that at 6, 0, we have a x-intercept, and at 0, 3, we have a y-intercept. And of course, you play connect the dots, and voila, you have a equation of a line. The last topic that we'll discuss is called the slope of a line, or finding the properties of the slope of a line. Now, basically, there exist many different types of lines that you could encounter, and slope is simply one of the properties that helps us differentiate lines from one another, or said another way, it helps us to determine the properties of the line itself. And in this instance, the slantiness specifically of the line. So slope is the same thing as the slantiness of a line. And you can think of this as a mountain climber who is embarking on a journey to climb a mountain. As he is climbing the mountain, if the slope is greater, the mountain will be more challenging to climb, meaning that as we increase the slope, the line becomes much more steep. So if m increases, m being our slope, then our line will become very, very steep. However, if m decreases, if the slope decreases, or as m decreases, as your slope decreases, your line becomes much less slanty for any equation y is equal to mx plus b. Now, of course, the question is, if you are given, say, two measurements along the line, say you are able to measure the maybe the base from the base of the mountain. Maybe this is we'll just say this is 100 and 0. Okay, we're at 0 feet of elevation when we make a measurement. And then when we start walking up the mountain, maybe we travel 200 feet up the mountain only to realize that we've gone a corresponding amount of distance in our horizontal direction. Okay, so as we're climbing the mountain, we're going in both a horizontal and X direction, as well as a vertical or Y direction. Okay, meaning going up into the sky. We're both moving in a forwards direction as well as in an upwards direction as we're climbing this specific mountain. And the question is, how slanty is the mountain itself? And one way to think about this would be to kind of draw ourselves a little bit of a picture here. I'm going to try to line up my points as much as possible. You think about how much vertical distance we've gone versus how much horizontal distance. Well, for my vertical distance, we went from 100, which was our starting point, to 400. For our vertical distance, we went from 0 to 200. Note that I'm getting these numbers for vertical distance as the y coordinate, which starts at 0 and goes to 200. If you were to take just a measuring stick and you measured from 100 to 400 and you saw how many units that happened to be, you would say, okay, that's the same thing as if I took 400 and I subtracted 100. Okay, imagine taking just a measuring stick and going from 100 to 400. You would be able to measure out exactly 300 units of distance. However, if that was feet, it would be 300 feet. If it was inches, it would be 300 inches, so on and so forth. It doesn't really matter the unit of measure. It just means, if you go from 100 to 400, you've actually gone 300 units of distance. And similarly, you could imagine taking a measuring tape and going from 0 to 200. And if you wanted to know how many units of distance you went, you would, of course, subtract 0 from 200, and you would get 200, a total distance of 200. Now, the slantiness of a line, the slope, interestingly, is always defined as and this is going to look a little bit exotic, the change of your vertical distance, which is represented by delta y, over the change of your horizontal distance, which is represented by this little triangle x. The triangle is delta, and it's just a shorthand for change. Okay, it's not that exotic. It just means the change of the vertical distance to the change of the horizontal distance. So this is the vertical distance to your horizontal distance. And we represent that by taking the final value of your vertical distance, in this instance 200, and subtracting it from your initial value of your vertical distance, which was 0. We'll use the letter y2 to represent your final vertical measurement. We'll use y1 to represent the initial vertical measurement. Similarly, we'll use x2 to represent the the final horizontal measurement, and we'll use x1 to represent the initial horizontal measurement. Now, students should know that 2y is not the same thing as y2. y2 is what is called a subscript. 2y is a number that's being multiplied by y. This is a coefficient. Okay, these are not the same thing. A subscript is a mathematical way of us saying that a one measurement precedes another or comes after or takes precedence over another. In this instance, we're saying the final measurement will always will always have taken away from it the initial measurement. So, if you had 200 and it was your final measurement and 0 was your initial, you're just going to take 0 away from 200. But then you do the same thing for your horizontal measurements. You're going to take your final measurement and you subtract the initial measurement from it. Okay, let's give some examples here. Say you have a question, find the slope of a line which passes through the point 2, 4, 5, 7. First of all, as you read this question, you need to underline the keywords. In this instance, slope. Slope means your m value for the equation y equals mx plus b. Okay. So think in your mind y is equal to mx plus b because we're talking about an equation of a line. And then we know the slope of the equation of the line is the m value. And then now we have a formula that represents the m value. We call it the change of the vertical over the change of the horizontal, or y2 minus y1 over x2 minus x1. Okay. Not too big of a deal. But where do we get the x2? Where do we get the y2? Well, basically, you have to choose one of these points to start with. You have to either say that this point here is my final measurement or this point here is my final measurement. Uh, I would usually draw an actual graph out. It doesn't have to be super exact, but this is just going to help you, stay organized a little bit. 1, 2, 3, 4, 5, 6, 7. So we have a point here, and we have a point at 2, 4. So that would be somewhere over here. And of course, we're going to have a line through this. So what are we measuring when we measure slope? We're measuring this little, we're taking a ratio rather of this little square, I'm sorry, this little triangular bit between these 2 points, 2, 4, and 5, 7. All right. I usually just take my second point and that becomes my second measurement. Okay. Like just for the sake of consistency, my second point just is going to be my second measurement. It really doesn't matter which point you choose because as it turns out, the slantiness of a line is constant across the entire line itself. Okay. It's across the entire line. The line's not doing some sort of wavy motion. It's just a straight line. So your slantiness doesn't change. It's constant across the entire length of the line forever and ever. Hence, you can pick any 2 points along the line. You're going to find the same slope at each point. And for whatever points you pick. So it really doesn't matter. Again, it does not matter which one is your x2, y2, y1, x1. All that matters is that when you pick a y2, the corresponding x coordinate pair is the x2. So for my second measurement here, 7, because I picked 7 to be my y2, my x2 must be the 5. I can't mix and match my x coordinates. It's not like I could say, okay, I'm taking 7 to be my y2 and then 2 is my x2. No. It's you picked this coordinate pair to be your second measurement. So the whole thing is the second measurement. All right, so it means that we have 7 on top, 5 on bottom. And then we have for our y1, that's 4. For our x1, that is 2. 7 minus 4 gives me 3. 5 minus 2 gives me 3. 3 divided by 3 gives us 1. So it turns out that the slope of the line in this particular instance happens to be 1. Some interesting things that students should know that kind of intuitively makes sense and actually makes the concept of the slantiness of the line intelligible is that just like a mountain, if you were trying to climb a mountain that went straight into the air, that would be really, really hard to do. So if you are dealing with a line that literally goes straight into the air. You say that the slope actually goes to infinity, because it's like you would have to be Superman to be able to climb this mountain, this sheer rock cliff, if you will. And similarly, if you have just a flat line, which goes off like that, then you've got a slope which equals 0. So for flat line, horizontal line, your slope is always 0. For a vertical line, your slope will be infinity. Always remember this. Put a star in this, because there might be a quiz question at some point or a test question at some point which utilizes these concepts. Okay, guys, that's all I've got for you today. Take care.